Early 1945. The waters surrounding Japan's coastline witness a dramatic scene. An American F4U Corsair plummets toward the ocean after its engine fails during a combat mission. The pilot ejects as his fighter slams into the frigid Pacific waters. Within hours, Japanese patrol vessels rush towards the floating wreckage. What they're about to recover will become one of the most significant intelligence prizes in the war's closing months. For nearly 3 years, Japanese airmen had battled this American fighter across the skies of the Solomon Islands, Rabaul, the Philippines, and now above their own homeland. They'd come to fear blistering speed, devastating firepower, and seemingly unbreakable construction. But they'd never possessed an intact example to examine closely, to measure precisely, to test thoroughly, and to understand just how far they'd fallen behind finally. The tale of Japan's encounter with the F4U Corsair goes beyond a simple story of a captured aircraft. This is the chronicle of a nation's technological awakening, the precise moment when Japan's aviation experts came face to face with the full scale of American industrial and engineering dominance. Through their meticulous study of this fighter, they would uncover truths about manufacturing precision, materials science, and design philosophy that would shatter every assumption they held about their own capabilities. The Corsair's design. The Corsair that Japanese recovery crews hauled from the sea represented the pinnacle of American fighter evolution. Born from a 1938 design to satisfy the United States Navy's demanding requirements, the F4U had transformed from a radical concept into one of the war's most feared combat machines. Its unmistakable inverted gull-wing design, the thundering Pratt & Whitney R2800 double wasp engine, and revolutionary performance made it instantly recognizable in any sky. More critically, it had achieved something Japanese aviation desperately struggled to replicate: a perfect balance of speed, firepower, range, and structural integrity. The Corsair's origins trace back to 1938, when the Navy's Bureau of Aeronautics issued a challenge for a fighter capable of exceeding 400 miles per hour in level flight. This specification alone was groundbreaking. Most fighter aircraft of that era barely reached 350 miles per hour. The Navy wanted more than just raw speed. They demanded low stalling speeds for carrier landings, a 1,000-mile range, heavy weapons, and bomb-carrying capability. Chance Vaught's answer was bold, almost reckless. Chief designer Rex Beisel and his engineering team made a radical decision: build the entire aircraft around the largest, most powerful engine available, the Pratt & Whitney R2800 double wasp. This 18-cylinder, 2-row radial power plant churned out 2,000 horsepower, nearly double what most contemporary fighters produced. To harness this immense power, they designed a massive propeller measuring 13 feet 4 inches in diameter, the largest ever mounted on a fighter. The engineering puzzle was immediate and daunting. How could they provide ground clearance for such an enormous propeller while maintaining the structural efficiency essential for carrier operations? The solution became the Corsair's signature feature. Instead of conventional straight wings, Beisel's team created an inverted gull-wing configuration. The wings angled sharply downward from the fuselage before leveling out, creating a distinctive M shape when viewed head-on. This unique design allowed relatively short landing gear while providing adequate propeller clearance. The anhedral angle where wings met fuselage also created optimal aerodynamic conditions, minimizing drag significantly. First flight and development. The prototype XF4U-1 took to the skies on May 29, 1940, with Lyman Bullard Jr., Vaught's chief test pilot, at the controls, lifting off from the factory airfield in Stratford, Connecticut. On October 1, 1940, during a test flight between Stratford and Hartford, the XF4U-1 achieved an astounding ground speed of 405 miles per hour with tailwind assistance, making headlines as the first single-engine American fighter to reach this milestone. The aircraft's actual maximum level flight speed was 378 miles per hour at 23,500 feet, still exceptional performance for 1940. Production. 4. U-1 Corsairs began reaching operational squadrons in late 1942. Marine Fighter Squadron, VMF 124, received the first combat-ready aircraft, deploying to Henderson Field, Guadalcanal, on February 12, 1943. Combat debut. The Corsairs' combat debut proved rough and humbling. On February 14, 1943, a day that became known as the St. Valentine's Day Massacre, Corsairs suffered a disastrous first engagement. 9 American aircraft were shot down, including 2 Corsairs, along with multiple P-38 Lightnings, P-40 Warhawks, and bombers, while Japanese defenders lost only a single Zero fighter. The 9-to-1 loss ratio in Japan's favor was so severe that daylight bombing runs to Bougainville were suspended while tactics were completely reassessed. This engagement hammered home a crucial lesson. Superior technology alone couldn't guarantee victory. Tactics, experience, and proper deployment mattered just as much. American pilots learned quickly from these painful lessons. They discovered that the Corsairs' true strengths lay not in traditional dogfighting, but in what became known as boom and zoom tactics. The Corsair couldn't outturn a Zero in slow-speed maneuvering, but it could outdive, outclimb, and outrun any Japanese fighter in existence. Proper tactics meant maintaining speed and altitude advantage, diving on enemy aircraft, firing devastating bursts, then using superior speed to break away before the enemy could respond effectively. Second Lieutenant Kenneth A. Walsh of VMF 124 became the first Corsair ace on May 13, 1943, mastering these aggressive tactics and ultimately achieving 21 victories. Growing reputation. As the war ground through 1943 and 1944, the Corsairs' fearsome reputation grew steadily. Marine squadrons in the Solomon Islands, operating from hastily constructed coral airstrips, exploited the aircraft's legendary ruggedness to devastating effect. The Corsair proved capable of absorbing battle damage that would have obliterated lighter Japanese fighters. Its 6.50 caliber Browning machine guns, the 4 inboard weapons carrying 400 rounds each, and the 2 outboard guns carrying 375 rounds each, totaling 2,350 rounds, provided overwhelming firepower. Later variants, like the F4U replaced the machine guns with 420mm cannons, though many pilots preferred the reliability and ammunition capacity of the .50 caliber weapons. The Corsair's versatility extended far beyond air-to-air combat. By mid-1944, Corsairs regularly carried external ordnance, 1,000 pound bombs on centerline and wing racks, 8 5-inch high-velocity aircraft rockets, or napalm canisters. This fighter-bomber capability made the Corsair invaluable for close air support during amphibious assaults. During the Okinawa campaign in 1945, Corsairs flew thousands of ground attack sorties, earning the affectionate nickname Angels of Okinawa from grateful infantrymen pinned down by Japanese fire. Japanese perspective. What Japanese pilots encountered in combat told only part of the Corsair's story. From the cramped cockpit of a Zero or other Japanese fighter, a pilot saw an opponent that was faster, stronger, and far more resilient. But truly understanding the engineering brilliance and manufacturing techniques behind these advantages required physical examination of the aircraft itself. Japan's capability for such technical analysis centered on 2 premier facilities: the Yokosuka Naval Air Technical Arsenal south of Tokyo and the Army Aviation Technical Research Institute at Tachikawa. These organizations had been studying captured Allied aircraft throughout the war, recovering examples from battlefields scattered across the Pacific. Their work had provided valuable intelligence about American capabilities, but most captures were damaged aircraft or incomplete wrecks salvaged from crash sites. An intact operational example of a frontline American fighter represented an extraordinary opportunity, a window into American capabilities they'd never had before. Yokosuka Facility. The Japanese Navy's Yokosuka facility had been conducting advanced technical research since April 1, 1932, when it was reorganized as the Kaigun Kokusho Naval Air Arsenal. By World War II, Yokosuka employed thousands of engineers, designers, and technicians. The arsenal designed numerous Japanese naval aircraft, though actual production was contracted to companies like Aichi, Nakajima, and Mitsubishi. Yokosuka's engineers were highly experienced professionals who understood aircraft design at the highest levels. When a salvaged Corsair arrived at Yokosuka in early 1945, it represented one of the most modern American fighters yet recovered in relatively intact condition. The aircraft had suffered water damage during its forced landing, but the basic structure remained sound. Recovery teams had worked frantically to prevent complete sinking, and the fighter was transported to Yokosuka's secure technical area for comprehensive examination. Initial assessment focused on overall condition. Despite saltwater immersion, much of the Corsair remained remarkably intact. The massive Pratt & Whitney engine would require complete disassembly and thorough cleaning, but the airframe structure showed no combat damage. This was absolutely crucial. Previous Allied aircraft captures often involved heavily damaged machines, making it difficult to distinguish design features from battle damage. Japanese specialists began with systematic photography and precise measurement. Every dimension was meticulously recorded: wingspan of 40 feet, 11.7 inches, length of 33 feet, 4 inches, height of 15 feet with wings extended, or 16 feet, 2.3 inches when wings were folded for carrier storage. The inverted gull-wing configuration immediately captured everyone's attention. Japanese designers understood the aerodynamic and structural advantages of this design, but they also recognized its staggering manufacturing complexity. Creating the compound curves and maintaining precise angles required sophisticated tooling and quality control far beyond what most Japanese factories could reliably achieve at this desperate stage of the war. The fabric surprise. The examination revealed something that particularly surprised the technical team. Despite the Corsair's advanced nature, portions of its outer wing surfaces were covered with fabric rather than metal. After the main wing spar and armament bays, both upper and lower surfaces used fabric covering, as did the control surfaces, ailerons, elevators, and rudder. Japanese aviation specialists initially found this puzzling. By 1944 to 1945, most modern fighters used all-metal construction. Further analysis revealed a sophisticated reality. The fabric covering was a deliberate design choice from the aircraft's 1938 to 1940 development period. It reduced weight where structural loads were minimal, saving precious aluminum for critical load-bearing components. The fabric was a specially treated material that, when properly applied, provided adequate strength and weather resistance while weighing significantly less than metal skinning. This represented a mature understanding of resource allocation for optimal performance. Wing structure analysis. Disassembly of the wing structure revealed construction methods that technical personnel found both impressive and deeply troubling. The main wing spar, the critical structural element carrying all flight loads, was a massive forging of exceptional quality. American metallurgy had produced aluminum alloy forgings with strength characteristics Japanese facilities desperately struggled to match. The spar's dimensions and load-bearing capacity exceeded anything in comparable Japanese fighters. This single component illustrated a fundamental difference. American industry could produce large, complex forgings with consistent quality, while Japanese manufacturers increasingly relied on built-up structures assembled from smaller components. The wing's internal structure demonstrated similar sophistication. Ribs stamped from an aluminum sheet showed remarkable precision and consistency. Each rib was virtually identical to the next, indicating manufacturing processes with incredibly tight quality control. Japanese aircraft production increasingly struggled with consistency as the war dragged on, with individual aircraft showing troubling variations in component quality. Armament examination. Attention turned to the Corsair's armament installation. 6 Browning AN/M .250 caliber machine guns mounted in the wings represented formidable firepower. The installation was compact, reliable, and designed for easy field maintenance. What struck Japanese examiners wasn't just the raw firepower, but the system's completeness. Ammunition boxes, feed systems, spent cartridge ejection, and charging mechanisms were all precisely engineered to work seamlessly together. The guns themselves were specimens of precision manufacturing. American ordnance production had achieved reliability levels that Japanese industry could only envy. The Browning M2 machine gun was a mature design, perfected through decades of development and manufactured by the millions with extraordinary consistency. Japanese technicians examining these weapons recognized manufacturing techniques and quality standards their own factories simply couldn't consistently achieve. Armor protection. The discovery of 150 pounds of armor plate, protecting the cockpit, and a 1.5-inch thick bullet-resistant glass panel behind the windscreen reinforced their impressions of American design philosophy. Japanese fighters had largely abandoned heavy armor protection in favor of lighter weight and better maneuverability. The Zero's early success validated this approach. But as American fighters grew more powerful and better armed, the lack of protection became fatal. The Corsair demonstrated that proper engineering could incorporate substantial protective armor without sacrificing performance. Possible by the massive power of the R2800 engine. The R2800 engine. That engine dominated the entire technical examination. The Pratt & Whitney R2800 Double Wasp represented American aero engine development at its absolute peak. 18 cylinders arranged in 2 rows of 9, displacing 2,800 cubic inches and producing over 2,000 horsepower. This engine was a genuine masterpiece of mechanical engineering. Japanese engineers had encountered this engine before in captured aircraft, but never had they possessed an example in relatively good condition for thorough analysis. The engine's construction revealed manufacturing capabilities that seemed almost incomprehensible. Cylinders were precisely machined, with tolerances measured in thousandths of an inch. Pistons, connecting rods, and crankshaft components showed surface finishes and dimensional accuracy that Japanese engine manufacturers struggled desperately to achieve. The 2-stage supercharger system, designed to maintain power at high altitudes, incorporated complex internal passages and precisely fitted rotating components. Japanese attempts to develop comparable supercharger systems had largely failed due to manufacturing limitations. Engine reliability. Perhaps most impressive was the engine's legendary reliability and consistent power output. American radial engines routinely produced their rated horsepower for hundreds of hours between overhauls. Japanese engines, even brand new examples, often failed to achieve their theoretical power ratings and required constant, frustrating maintenance. The R2800's consistent performance came from superior metallurgy, better lubricants, more precise manufacturing, and far more sophisticated quality control, advantages that seemed insurmountable. Propeller system. The propeller system proved equally revealing. The Hamilton Standard Hydromatic propeller, with its 13-foot 4-inch diameter and variable pitch capability, represented advanced aerodynamic design and sophisticated hydraulic control systems. Japanese engineers understood propeller theory perfectly, but lacked manufacturing facilities capable of producing large propellers with the necessary precision. Systems analysis. Examination of systems throughout the aircraft revealed consistent patterns. The landing gear mechanism was complex, but precisely manufactured. The cockpit instrument panel presented a comprehensive array of gauges and controls, exceeding anything in Japanese fighters. The fuel system incorporated self-sealing tanks using multiple rubber compound layers that swelled when punctured, preventing catastrophic fuel loss, a technology Japanese aircraft largely lacked. The electrical system powered extensive equipment through high-quality wiring, with proper insulation and organization. Manufacturing quality. Perhaps most revealing was the overall quality of materials and manufacturing. Every component, from major structural elements to tiny fasteners, showed consistent quality. Aluminum alloys had uniform properties, steels were properly heat-treated, surface finishes were smooth and professional. The aircraft felt substantial, well-made, built to endure. This overall quality stood in sharp, painful contrast to Japanese aircraft production in 1945. Wartime shortages had forced increasing use of substitute materials. Aluminum quality had deteriorated badly. Skilled workers had been conscripted for frontline service. Factories operated under constant threat of American air raids. Quality control suffered dramatically as production schedules demanded quantity over quality at any cost. The desperate context. The examination of the captured Corsair occurred as Japan faced imminent, inevitable defeat. American B-29 bombers were systematically destroying Japanese cities. The Navy had been shattered at Leyte Gulf. The Philippines had been liberated. Iwo Jima had fallen, and Okinawa was under brutal assault. In this desperate context, the Corsair examination took on somber significance. It wasn't intelligence gathering for future victories, but a final reckoning with technological reality. Japanese engineers at Yokosuka and Tachikawa wrote detailed technical reports documenting their findings. These reports meticulously detailed measurements, described manufacturing techniques, and offered frank assessments of American capabilities. The tone was professional, but couldn't hide the underlying implications. In nearly every category examined, American technology exceeded Japanese capabilities. The gap wasn't small or easily closed. It represented years of industrial development, massive investments in research and tooling, sophisticated supply chains, and resources Japan simply did not possess. Captured Corsairs. By war's end in August 1945, at least 2 Corsairs had been captured by Japanese forces. Evidence suggests technical personnel repaired at least 1 aircraft to flying condition, as photographs show captured Corsairs with patched wings and fuselages. Whether actual flight testing occurred remains uncertain, but repair attempts indicate serious efforts to make the aircraft operational for evaluation. When American occupation forces arrived at Yokosuka Naval Air Technical Arsenal in September 1945, they found extensive evidence of Japanese technical intelligence efforts. Captured Allied aircraft were scattered around the facility. Technical reports, drawings, and photographs documented Japanese attempts to understand Allied technology. American intelligence officers collected these materials, recognizing their value for understanding what Japan had learned. The bigger picture. The story of the Japanese examination of the F4U Corsair represents more than technical intelligence. It symbolizes the vast gulf separating American and Japanese aviation by war's end. When the Corsair first entered combat in early 1943, Japanese pilots in Zero fighters could still compete effectively through superior tactics and pilot skill. By 1945, even experienced Japanese pilots in more modern aircraft stood little chance against well-flown Corsairs. The aircraft's technological advantages, combined with overwhelming American numerical superiority and superior pilot training, created impossible odds. The Corsair achieved an official kill ratio of 11-1 against Japanese aircraft. American pilots flying Corsairs shot down 2,140 Japanese aircraft, while losing only 189 Corsairs to enemy action during World War II. These numbers reflected not just the Corsair's technological superiority, but the entire American war machine's advantages: better training, superior logistics, overwhelming production capacity, and advanced technology at every single level. Japanese understanding. Japanese engineers examining the captured Corsair understood all of this with painful clarity. They could measure the performance gap, analyze the manufacturing differences, and calculate the resource disparities. Their reports documenting these findings stand as acknowledgments of Japan's failed attempt to match American industrial might. Post-war Corsair service. The Corsair itself went on to long, distinguished service beyond World War II. It fought in the Korean War from 1950 to 1953, where it proved highly effective in ground attack and close air support roles, even as jet fighters took over air superiority missions. Foreign air forces, including France, flew Corsairs in colonial conflicts through the 1960s. The last combat missions by Corsairs occurred in July 1969 during the brief soccer war between Honduras and El Salvador. On July 17, 1969, Honduran Captain Fernando Soto, flying an F4U-5, shot down 3 Salvadoran aircraft, including 2 FG-1D Corsairs. The final combat victories for the type, ironically achieved against other Corsairs. From its first flight in 1940 to its final combat missions nearly 30 years later, the Corsair proved one of aviation history's most successful and long-lived fighter designs. Japanese post-war transformation. For Japan, the encounter with the Corsair was part of a larger reckoning with technological reality during the American occupation. Japanese engineers and scientists who had struggled against material shortages and industrial limitations during the war now worked with American occupation authorities to rebuild Japanese industry. Lessons learned from examining American technology, including the Corsair, influenced post-war Japanese manufacturing philosophy profoundly. The emphasis on quality, precision manufacturing, and continuous improvement that characterizes modern Japanese industry has roots in the hard lessons learned when Japanese engineers examined what American industry could produce. Closing reflection. The Corsair, recovered in early 1945, represented more than a downed fighter. It was living evidence of engineering excellence and manufacturing sophistication that Japanese aviation had been desperately seeking throughout the war. The lessons it taught came too late to change the war's outcome, but they helped shape the peace that followed. In examining this American fighter, Japanese engineers confronted the full magnitude of the challenge Japan had faced. They had fought with tremendous courage and skill, but courage and skill couldn't overcome the massive technological and industrial advantages their opponent possessed. The story ends not with triumph, but with acknowledgement. Japanese technical reports on the Corsair, discovered by American occupation forces and now resting in archives, serve as silent witnesses to a moment when one nation's engineers confronted another nation's capabilities with unflinching honesty. The Corsair they examined has long since vanished, likely scrapped during the chaotic post-war period. But its legacy remains in the lessons it taught about what technology, properly applied with adequate resources and sophisticated manufacturing, could achieve. Japanese aviation would rise again in the post-war era, but never again would Japanese engineers underestimate what their American counterparts could accomplish when given the industrial capacity, scientific knowledge, and resources to realize their designs fully. Final words. The examination of the F4U Corsair by Japanese technical personnel in 1945 stands as a watershed moment, the point when Japan's aviation establishment fully grasped the technological chasm that had opened during the war years. It was a lesson written not in propaganda or combat reports, but in aluminum alloys, precision forgings, and manufacturing tolerances that spoke louder than any words could about the true nature of American industrial power. This wasn't just about one aircraft, it was about understanding, finally, completely and undeniably, the price of technological complacency and the power of industrial might.